In this video, I'm going to look at some applications of systems of equations. Let's jump right into it. Solve the following application problems. 3 times a number, 3 times a number less a second number is 1. The sum of the number and twice the second number is 13. What are the two numbers? It's always a really good idea just to start off by labeling what things are representing. So I'm going to let x represent the first number and y the second. This makes it a lot easier, one, when we're setting up our equations, and two, when we're trying to figure out what the things we just found were. So take that first statement, 3 times a number, first number, 3x, less a second number. Well, less means minus, that's equal to 1. And then the second statement, the sum of a number and twice the second number is 13. The sum means we're adding the number and twice the second number. So that'd be 2y, that's equal to 13. That's all there is to that one. Once we have it set up this far, then we are going to solve it using substitution or elimination. In its current format, with those x's and y's saying one on top of the other, I think that elimination is going to be a little bit easier. So I'm going to choose to eliminate the y's. Why am I choosing the y's? Well, just because they already have opposite signs. We have a minus and a plus. Could have just as easily multiplied the second equation by 3 to eliminate the x's. So I'm going to multiply the first equation by 2, and I get 6x minus 2y equals 2. And on the second equation, I have x plus 2y equals 13. To get those y's to eliminate, I'm going to add the two equations. I'd get 7x, y's are canceling, equals a 15. To get the x's to go away, to get the x's by itself, I need the 7 to go away. I'm going to divide by the 7, so x is equal to 15 over 7. And so there is one of our variables. Now that we have the first variable, we need to solve for the second variable. Well, I can take any of these equations to plug back into, makes no difference. I'll plug it into this equation right here for no reason at all, other than it's just nice and black. Say 15 over 7 plus 2y equals 13. I need to start by subtracting the 15 over 7. So 2y is going to be equal to 13 minus 15 over 7. And I'm going to use fractions just to make it a little bit cleaner, in my opinion. So we'd have 76 over 7. And then we need to divide by that 2. And that will give us 38 over 7. So now we have our two numbers, 15 over 7 and 38 over 7. Last thing I want to do is just to explain these, right? I need to state which one is which. So the first number is 15 over 7, and the second number is 38 over 7. We always want to explain what our answers meant. So that is a very, very basic application. We didn't really have any meaning built around it other than just the numbers. Let's move on to a more meaningful example. So trail mix contains peanuts and raisins. I'm going to start by just labeling my variables. Peanuts, raisins. Peanuts cost $3 per pound. Raisins cost $1.50. To a mixture is $27. 3 more pounds of peanuts than raisins. How many pounds of peanuts and raisins are there? So $3 per pound on the peanuts, that'd be 3x. Raisins are $1.50 per pound, that'd be 1.5, 1.50y. Obviously, if we're getting to a total cost, we're adding these two sub-costs. That total cost is getting us to 27. I'd point out I could do a very similar thing with the mixtures like I done in class, where we're mixing two things together. Just rather than having percentages of acid or gold or whatever our mixtures might be, we're dealing with amounts, dollars of amounts. So $3, $1.50. And over here, this total cost, this whole thing would be 27. It's not just of that, per pound, that's the total cost. So it's $3 of X, 150 of Y, to give a total amount of cost of 27, not just 27 inside the cup, but the total thing. So that would be our first equation. The second equation, there are 3 more pounds of peanuts than raisins. So a lot of times the way I'll kind of start by thinking about this is, just set X and Y equal to each other. this is obviously not a true statement because there's more peanuts. There's more in this first thing, this left-hand side, than there is on the right. So I'm saying these two things are equal. If they're going to be equal, that means I need to add 3 to the y to make the two sides match. There's more over here. If I'm thinking about this in terms of those balance beams ideas, there's more weight on x's side than on y's side. So I've got to add that 3 over here to bring the equation back into balance. Or, kind of reading the words very directly, 3 more pounds of peanuts than raisins. So peanuts are 3 plus the raisins. And so there would be our second equation. In this case, because of the way I have it set up, I think substitution is going to be the easiest. So I'm going to take the y plus 3, I'm going to plug it in for the x. So 3 times y plus 3 plus the 1.5y is equal to 27. I distribute 3y plus 9 plus 1.5y equals 27. I'm going to combine my like terms, so I'd get a 4.5y. I'm going to subtract that 9 over. 27 minus y is 18. When I take the 18 and divide it by 4.5, I get 4. So y is equal to 4. My y is equal to 4. I still need to find the x. We'll have an x equation right here. X is equal to 4 plus 3. And 4 plus 3 would be equal to a 7. So now we have our x and our y. But again, we need to describe what's going on in this situation. X and y is meaningless. So this tells us there are 7 pounds of peanuts and 4 pounds of raisins. So that would be our final answer there. Let's look at one last word problem. You drive at 51 miles per hour on your way home to compete in a cycling event. You ride your bicycle at a rate of 3 miles per hour. You traveled a distance, total distance of 19.25 over a time of 65 minutes. That's together both the car and biking. How far did you travel while biking? I'm going to set up a picture to kind of help me with this. We're going somewhere and then we're going further, but the two different rates are different, right? The rate at first was 51 miles per hour. The time, we don't know. The rate while biking was 3 miles per hour. We do know some overalls. The total distance was 19.25, and the total time is equal to 65 minutes. We don't know those individual distances. So let's think about some ways we can relate these variables. Well, we should know in a basic equation, distance equals rate times time. I know the total distance. I don't know these individuals. So it would really help to kind of figure out these sub-distances. How far is this distance? How far is this distance? And then together, those two distances, I'll call them D1 and D2, have to be equal to the 19.25. So if we think about distance 1, well, that would be equal to the rate, which we know, 51, times T1. Distance 2 would be equal to the 3 miles per hour times T2. We don't know either of those times, but we know that 19.25 would be equal to 51 T1 plus 3 T2. Could have used X and Y instead of D1, T1s. I'm just using that to represent kind of, because these variables have meaning, because there's times and distances, using the 1s and 2s just to represent, you know, that first leg of my journey, the second leg of the journey. So I haven't officially labeled these variables in the same way I did here. We've kind of done it graphically with the picture and just knowing that the letters have meaning. All right, so I have my first equation. I need my second equation. Well, T1, T2 are the unknowns. I know that total time is 65. So together, those two elements have to add to 65, kind of, because remember, these rates were miles per hour. This time is in minutes. So the first thing I need to do is I need to convert that time to hours by dividing by 60. So you can reduce that if you want. You could just leave it as a fraction. It doesn't matter. It's probably a little easier to work with it as the reduced fraction. 13 over 12. And so that gives me the second equation. 13 over 12 is equal to T1 plus T2. Those two times together add up to the total time it took me on my trip. Could use substitution or elimination because of the way it's set up with the T1s, T2s sitting one on top of the other. I think it's going to be a little bit easier to use multiplication. So I'm going to multiply by, it's elimination. So I'm going to multiply by 3, so I kind of get those T2s to cancel. So top equation is staying the same. Bottom equation, we're going to have 13 over 4 when we cancel out. 3t1 plus 3t2. And I need to subtract in order to get those t's to eliminate. I could have also multiplied by the -3, and then they would have canceled directly, but here I have to subtract because I just used the same signs. So I have 19.25 minus the 13/4, and that gives us 16. 51 minus 3 is 48. And then the T2s cancel. So to get T1 all by itself, I'm going to divide by the 48, 16 over 48, which would simplify to a third. So T1 is equal to 1/3 of an hour, also equal to 20 minutes. We need to figure out what T2 is. And remember, we have this equation right here. T1 plus T2 equals 13 over 12, so is equal to that 65 over 20, or 20 minutes. So we could also just subtract from the 65 minutes. However we want to do it. I'm going to stick with the hours for just a second because that's the direct answer we found here, 1/3 of an hour. I'll plug in that 1/3. Going to subtract that over. And that would be 9/12, which simplifies to an exact 3/4. And again, both of these are hours because that's what our miles per hour had been. We converted that time of the 65 minutes into hours to get our units to match. So these are both hours. So now we can state that it would take us 1/3 of an hour. We took 1/3 of an hour, or this individual took 1/3 of an hour in the car and 3/4 of an hour cycling. All we really care about is the distance traveled while biking. We didn't actually care about the times. I care about the distance. And so I'm curious about this thing right here. And we know that D2, that was when we were cycling, 3 times 3/4. And so that would give us 9/4 miles, which is, of course, 2 1/4 miles. So you will travel 9/4 miles biking. There's our answer. So with these word problems, it really helps to set up a picture or define those variables early on, or maybe even do both. But define those variables, set up those pictures, and then from there, we can set up our equations, we solve them, and make sure that you always go back and reread the problem to make sure we have actually answered what the problem wanted us to find.